Welcome, accepted students. My name is Professor Shayla Sawyer, and this is my presentation on some of the research that's going on in my lab. So, it's important to know that I was once sitting in your shoes not too long ago. I still consider myself to be youngish, a little bit about me. And I was an RPI graduate student. Technically, I'm a millennial, like right at the edge of that, right in the beginning. So I'm not too far from you guys. When you see me, you'll know who I am pretty quickly. I'm a rather tall African-American woman, and I'm pretty busy. So if you hear my kids in the background or my husband or something while I'm making this video, it's because I'm busy all the time. There's always something going on. But I say all that to say, all right, you'll know who I am. And one of the most important parts, even though I have a lot of things going on in my life, I really love the things that I'm doing. I'm doing what I really want to do. And it's fun and exciting. And a lot of that came out of an RPI PhD education with the colleagues that you will see. So what exactly do I do? To go through this briefly, it all came from just a basic idea that kind of went through this process. And in summary, it's the idea from undergraduate, my undergraduate education at Hampton University, my home by the sea, a historically black college and university. A couple of things came out of that. I was an athlete, student athlete, a basketball player, and I was very interested in kind of the dream of nanotechnology. The idea of nanobots in the body was kind of like an amazing thing that I was interested in. And because of that, it's the reason why I went to graduate school, to understand at least some of the physics of small things. And because of the fellowship that I came in under, I then wanted to use those small things to track biological things. And in doing that, because of my experience as a grad student, because of my fellowship, I had internships that corresponded with my thesis work, and my advisor was awesome, Professor Michael Shore. My advisor worked really well with me in these goals, and I was able to do both. Do research, work on internships, and kind of develop myself in that way. But in doing so, I learned a lot about systems and how my research fit in, and that maybe it wasn't a major problem. Maybe my research, which was on LEDs, maybe I could switch over to the sensing side, and that became the foundation of my professorship. And through that, I decided to basically center the type of work I do around the idea that maybe I can use synergy or synergistic materials to work together to outperform materials that are perfect, so to speak, and or materials that don't have a whole lot of defects. And so these two questions became a little bit of the foundation of the work that I do. And if you think about it, being a student athlete, it's very much like a team aspect. Yeah, that's me. But back in my college days, playing a sport. So now this is my current research family that have been doing amazing things with that fundamental idea, and continue to do that work as we work through these ideas. And so again, some of my students recently, and some from a little bit while back, very proud of their accomplishments thus far. So my students are kind of span this spectrum from the foundation of what I was working on as a PhD student here at RPI, which was LED devices and characterization, specifically signal to noise ratios, or low frequency noise, of materials that make light emitting diodes. And that is expanded out into this. So now I work very much on the detection side, or the detection of light, and integrating nano biomaterials, new kind of combinations of those, into devices that sense light, and then marrying those into larger systems. And so a lot of the work now goes into designing devices and sensors using these unique materials. All right, so here are some of the systems. Imagine if a hospital room could detect bacterial contamination and kind of mitigate itself. And this is in large part due to the center I'm associated with, a lighting-enabled systems application center, and we are working on ways for the room itself to be smart enough to mitigate any dangers that's in it. Obviously, this type of work is kind of apropos to what's happening nowadays, even though it's viral, which is different. The idea that you could detect that something's wrong on a surface and kind of kill it when you see it is the fundamental idea. And we do that using light. Other things, when it comes to any type of natural disaster and you have a potential bacteria rise, then there's a possibility of sensing problems in water, such as flood water, and having collaborations with people who do that kind of work. And while we're in water, there's the idea of doing water quality sensing in general. And so my research is associated with the Jefferson project here on campus, and it is a collaboration between Rensselaer, IBM, and the Fund for Lake George. And the idea is to kind of combine all of these data streams and all of the sensing capability on this very high-tech lake to try to predict things that are happening in natural waters. One thing that's really important is the idea of these harmful algal blooms, and they kind of show up and disrupt a lot of things. And if we can predict why they're happening and what nutrients are feeding them and where those nutrients are coming from, it could really change things. So they are very much interested in some really innovative phosphate sensors that are cheap, real time, and ideally don't have a whole lot of reagents or no reagents at all. And so when we were trying to make sensor systems, we deployed these very kind of low cost, do-it-yourself, open source SONs that we developed. My undergrads put together in collaboration with CATS. They put together these systems where you can use commercial sensors and attach them to the system to use them in water quality sensing. And so over the summer, these high school students built the entire system and were able to calibrate the sensors and put them in Lake George and monitor the data that was collected in real time or near real time. So that was great. All right, so that's all the system stuff. And my undergrads tend to really focus on the system stuff. It's really applied. When it comes to materials and devices, my grad students do that kind of work. And so this is just kind of a spattering of some of the devices that we've created in my lab. Again, like I mentioned before, we started moving towards sensing and these really combining materials in a unique and synergistic way. And by doing so, we were able to make very sensitive detectors at very specific wavelengths by combining materials. This is another device that, it looks kind of like a human hair. Not exactly, but it's a hybrid fiber made of perovskite materials. And it performs very well and has a great response time as well. So sensitive plus fast plus cheap equals work on a patent for that. And yeah, we're doing that. It's an interesting system to work with. Another interesting system to work with. That thing on the left looks very strange, I'm sure. yes, those are bacteria. And the question is, do you know that bacteria talk to each other? Yeah. So that's a thing. Bacteria are able to pass electrons to each other through extracellular electron transport. And when they are stressed, they form biofilms, and they survive by essentially breathing metal, and instead of breathing oxygen. So they can breathe metal, and you can do lots of things with that. We intend to use them to help us sense things like phosphates in natural water, or many other things, because we believe or imagine that they are highly sensitive to things that inorganic things cannot sense. If we can talk to them or watch the electrons pass, and kind of interface with them electronically, so to speak, we can have a very sensitive living sensor. And we're working on that. And so there are a couple of things that we hope to do with these very unique bacteria. They are dissimilatory metal reducing or dissimilatory sulfur reducing bacteria. We're interested in doing three things with these bacteria. One, hacking the bacterial nanowires. Two, using them as bacterial nanofactories. In other words, have them create the nanomaterials for us at room temperature in large batches. Or three, actually having them be a part of a sensor. And then finally, I am an experimentalist, but I do really need and like to work with people who are computationally minded and who work with simulation. And I have a student, Amelia Peterson, PhD student, working with us, the crazy experimentalists, to try to help us get into more simulation and computation, and so that we can have some kind of prediction and control. And so she is working on modeling some of our early devices that, again, they work with, there are kind of chemical surface reactions that are happening that we need to make sure that we are simulating in order to predict the device performance. And so she is working on essentially building the simulation framework for us to predict things. And so she was doing great work with Centaurus, MATLAB, and kind of integrating new models that are found in other disciplines in order for us to get more accurate device prediction. All right, so that's my research. I don't want to spend too much time, but there's a whole journey, and I'll be glad to share those things with you. But I think if you're here for grad school and if you are want to attain a PhD, the PhD is not necessarily just a degree. It is a process with lots of ups and downs and lots of things that you will learn, and the process is what you will hold with you as well as the knowledge. And so remember that the PhD is a process. It prepares you for many things. So with that, if you want to contact me, you can find me online. You can email me. I'll be glad to talk with you. Okay, thanks.